Hello, everyone. Yes, I'm Marcin Ziemiński. I'm working at Ntropy as a machine learning engineer, and I'm really excited to show you how we herd entities at Ntropy, or in other words, how one can design entity search system for transaction data. So first things first, who are we? So at Ntropy, we work on transaction intelligence. We enrich transactions. That is, we try to extract some valuable data from those transactions, build some interesting insights that we can pass further. So what does it mean to enrich a transaction? On the right-hand side, you can see an exemplary transaction. On top, it is given basically just a plain text as a description. From this description, our goal is to extract some information. For example, who the merchant is. In this case, it's KFC. We find out what's the logo, the website. We are sometimes able even to extract location based on some hidden store IDs that are present in transaction descriptions. We also can take a wider context of transactions history of a particular history of transactions, and check if the given transaction is a recurring transaction, is it a subscription or just one of thing, and additionally we are able to categorize transactions, and all of that can be achieved, can be obtained with just a few lines of fairly simple Python code. The only thing you have to do is import your CSV file, can be pandas, import our SDK, use literally one line of Python code, and voila, your transactions are enriched. They should have all of this interesting information. So let's look under the hood, how the system is structured when it comes to the key steps. And on the top, you see that there is a transaction. The first step is a named entity recognition model, which looks at the description and tries to assign some classes to the substrings within this transaction to locate pieces which may correspond to some real-world entities. It also classifies dates, detects locations, and still it's not enough, right? It's just some pieces of strings. So we have to do a full entity search where we are to find out who these entities really are, find out their names, websites, tags, what you've just seen on the previous slide. Only after that, we can do more high-level analysis such as categorization, recurrence, and so on, and so on. So for this talk, I will focus on the middle piece, on entity search, which is really a precondition to these higher-level tasks. Without it being performant and correct, anything can happen later. So we have to make sure that it is done right. And besides our clients, the users of the API are also interested in the direct outputs of this step. So what are entities for us in the context of transactions? So they can be some organizations such as Amazon, government institutions like IRS, or they can be concrete services that these organizations provide, like YouTube TV, Amazon Music. The other kinds of entities are physical places, some restaurants around the corner when someone paid for lunch. Entities can also be politicians or freelancers, politicians who get donations for their campaigns. So we have to resolve all of that. But these entities, they don't live in some space. They live in the context of a transaction. That's why they have different roles as parties of this transaction. So there are merchants, there are also intermediaries such as payment processors like PayPal, or delivery platforms which stand in between the hungry customer and the restaurant. And yeah, herding entities, doing entity search is a really difficult task, but this makes my work interesting and challenging. Why is this so difficult? Because there is no industry-wide standard for transaction data. There is no protocol of exchange of information that would contain all the information on those entities. So we have to work with the small common language, which is basically plain text description, some amount, some meta information, very basic, like currency or country. On top of that, the language of those description is just a language of its own. So there are some patterns that are inherent only to transaction data. So for example, you might find a pattern PP and you have to know that it stands for PayPal, right? It's basically the only place where you see this kind of patterns. There might be an entity that's called, for the sake of argument, some great company Inc. with its website. It may be present in many transactions that we have, but the name or its website is completely distorted, right? Some vowels might be lost. There is a high degree of truncation. Sometimes there's just an acronym for a given name. The other times, the entity can be determined only indirectly through the product that they provide. And after all this loss of information, the patterns that we're left with are quite ambiguous. So you may see CK and you don't know what does it stand for. Is it Circle K or maybe Calvin Klein? And in addition to that, sometimes you would like to see nice locations with a full address, but most of the time, the most interesting piece is cut off. So yeah, this diagram is an abstract overview of how entity search system at Ntropy works. I mentioned the first step was named entity recognition. It gives us a list of organization candidates and the location string from those transactions. Those are just simple substrings. Then we would already like to run a full search using these substrings, but we have to stop ourselves because we don't have all the time in the world to do that, and all the resources, right? There is an inherent cost to these searches, so before that happens, we have to estimate the budget, maybe using some tricks, some metadata that we have. After that, we can finally run entity search for each of these entity candidates. It is done independently, can be run in parallel. Moreover, if location is specific enough, it might be enough of information for us to determine who the entity is, right? So from this from this step, we get for each candidate a list of entities together with the scores that we assign to them. So finally, the goal is to select from these candidates the final solution that's the list of entities with roles assigned to them, right? So we have to find out who the merchant is, who the payment processor might be. It might happen that we're unable to do so because maybe we might have estimated the budget, the resources that we need for that incorrectly, so we have to re-estimate that, obviously on condition that we still have time and some resources, and do the search in a loop again. So what's about this budget? The thing is that our system, it may run in two different modes, real-time, batch. They have different constraints, and we really have to answer some of the questions, like how much time we can spend on each query to every search engine, how many query results from one single engine we can process, right? It may involve some model executions. Maybe we should only limit ourselves to cached results from those search engines, because there is not, because they incur some cost and they take time to execute, right? And we have our database. We call it domain metadata database, which contains different kinds of patterns, some domain knowledge that helps us to do so. So, for example, there might be a pattern for which you know that it always resolves to a given website, so there is no need to do a full search. The other times, different kinds of patterns might be indicative of the merchant behind the transaction, which is usually the most important party within the transaction, so we know that we have to spend more resources on that particular pattern. So let's focus on a single pathway. Let's say we're considering just a single organization candidate. Maybe we got a location string from there too. So we run multiple search engines. and concatenate all of the results together, and they form triplets of queries that we used to search for a given thing, resulting entity and some metadata that we add for each search engine, which might be very useful later for ranking because we cannot treat all of them equally, right? So we got lots of results, lots of, I don't know, it might be just 10 in total, it might be 50, but there might be some duplicates or in general entities which correspond to the same underlying entity in the world. So we have to group them together and assign the entire group, and you score some confidence estimates. And this is also the step where we reject entities or the entire groups before we move forward. So let's say we got those groups. In each group there are different entities. Still, this is not something that we want to return. We're not returning lists. We have to return a single representation of a real world entity. So we have to look up maybe some additional information on this entity and then merge all of that together to get the final name that we want to return, the final website, and so on. Let's go even deeper. So let's just focus on search engines, right? We get, again, organizational location that we want to search for. And there are different search engines. They have their own characteristics. So based on that, we might construct the queries differently because we know that one particular search engine responds really well to some kind of query. Sometimes it might be beneficial to append a location string during the search and so on and so on. So for each search engine, we may have multiple queries. We run them, select top K results for each of them. Then the results are concatenated, as I just mentioned earlier, with some metadata information on each search engine. So let's talk about search engines. What kind of search engines we might use to find entities for transactions? We can break them down by different aspects. So there is always this dilemma. Should we use a service that's externally provided or we should build our own? So what are the pros and cons of both? For external services, these are huge systems, huge distributed systems. Many people work on them. They usually have a very high coverage on entities. So if there is an entity that has a website, whatever, it's for sure somewhere searchable using these different search engines. The data is up to date, right? When I set up a new company, or I usually try to get it indexed as high as possible so it's searchable. But unfortunately, the cost may be high of running all those queries through these search engines. The latency is unpredictable, and we at Ntropy have to enrich transactions really, really fast. And they only just give us some results sorted by some scores that we don't have access to, so we cannot make use of them. On the other hand, we can have an internal engine that can be adjusted to our concrete case, right? We may use of some domain knowledge. Maybe you can also utilize the labeled data of transactions to boost search results for certain kind of queries. We can control the cost, scale the system easily, right? But no matter how good our algorithm is, it will not be better than the underlying data that is based on. So we have to pay a lot attention to curation of entity data. And obviously, there is a cost of maintenance and research of such a system. So yeah, I talked about some external engines. An example of them is just the web search engines that everyone should be familiar with, like Google or Bing, right? As I mentioned, the data is up to date. The results can have virtually anything. They are very fine-grained. They are not just high-level organizations. We can get results on a particular service like Amazon Prime, Xbox Live, and so on. Another interesting property of this kind of search engines is that they also give us results from aggregator websites such as Yelp, Facebook, and LinkedIn. And if you think about them, these websites are basically entity stores and entity search engines. So we can take advantage of them for our own purpose. Another really good property of these engines is that they're correlated with financial data. So let's say there is a company, this company grows, advertises its products, people pay for these products, then we see transactions with these entities, we search for them, and yeah, they're on top of search results, right? So there is this correlation with financial data that is very beneficial for us. But there are also problems with these search engines. The data that we are looking at is very simple. I just URL is the title, just as you can see on the picture, and some snippets. So we have to extract key information, name, and some tags, which might be useful for downstream tags. On top of that, these results are extreme noise. They can be anything. So you know, because you use these kind of search engines every day. And even if we find the right thing, quite often the snippet that should describe this thing is very uninformative. It's completely useless to us. So might be quite misleading. And there are also some entity search engines available as APIs. They give you nice structured data with most of the fields that you would be interested in. And when you search for entities, you get entities. You don't get websites suggesting baby names or funny cat videos, which might be very annoying and difficult to handle automatically. But the problem is that you search engine for entities and you get entities sometimes when you shouldn't really, right? Because there the first model is not perfect. It might create some suggestions that are not correct. Still, we get an entity which looks really nice in structured data, so it's difficult to automatically reject those examples. And yeah, we rely on the quality of the entity data that these search engines are based on. And usually they are only focused on high-level entities, not concrete products, right? So the company may come up with a new product that's only popular for a certain amount of time, then it dies, and there is another product that these search engines, they only have very high-level information. So I mentioned that we really have to optimize cost and time. So we use Scylla for that. We cache every query to every external API. We cache it by the query itself and all the parameters that we used to do the search. And we do it always. So even if the query hits a timeout and we have to move forward, we still cache the result. And we do it in the background so that it can be used later and we don't waste all those calls and money at the same time. And we also use this neat trick, this clever trick for fuzzy caching. So it may happen that the thing is not in cache. We are short on time. What do? We might find the query that is very similar to the one that we're running right now in cache. We use Elasticsearch for that, which is a basic thing, but one has to be really careful with that, not to let in the results which are really too far from what you're interested in. And we built our own internal search engine, but it's really a full-blown entity service. It's really an entity store that is, it contains all the entity data that we have, and we can manipulate this data. If there is a customer request saying that the name of this company is not exactly right, there is something missing, we can add it there, right? So we can control this database, and on top of it, we have an entity search algorithm which makes use of the label data, the domain knowledge that we have, all the databases that we built over time. So the index for search is based on Elasticsearch, which is a text-based search engine, and Milvus, which is a vector database and nearest neighbors search on top of it. So the core flow on this entity search algorithm is very basic. As usual, there's the first step, which does the retrieval thing. It has to have very high recall, so that the thing that we're interested in is always within the results. It must be simple and fast. Then our goal is to just prune the incorrect results, keep recall as high as possible while increasing the precision. So let's talk first about the index that we built using Elasticsearch. We try to utilize every possible field that describes a given entity, because this is how these entities end up in our transaction data. So for name, we do lots of processing, remove redundant suffixes like LLC standing for limited liability company, We also have variations of names without vowels, and we use another thing that's helpful with fuzzy matching. That's phoneme encoding of names, so that different patterns get the same encoding, even though they're spelled differently. The encoding is based basically on the sound that they would make. We add their market tickers to the index, because this is also what we see sometimes in transactions. We inject many different variations of the website belonging to a given entity. Part of this index is devoted to locations search, and as I mentioned, we try to make heavy use of labeled data that we have. Let's say there is a transaction that should be for which the merchant should be DoorDash. In this transaction, we realized that DD or DO or D corresponded to DoorDash, which is the entity behind it. So we added to the index such that next time we see a similar transaction, the DoorDash pops up higher, making use of this labeled data. But unfortunately, Elasticsearch is not perfect. It falls short at our crazy level of fuzziness. And if you want to catch all those different patterns, still having high recall and precision, you really need to solve lots of puzzles. Try to use n-grams, enable some fuzzy matching and Elasticsearch, and in the end, the index gets really slow, difficult to manage. So because of that, for those hard cases, we turned to Milvus. So how does it work? Sorry, how does it work? So the approach is quite similar as with Elasticsearch. Given an entity and different fields that it consists of, we embed all those fields, getting some vector embeddings. For that, we have models based on fasttext or TFDF, trained on character level n-grams. The goal is not to have embeddings which are semantically similar, but we're most interested in lexical similarity, just based on characters. So then we get a query, use the same algorithm to embed the query, run an approximate nearest neighbor search, and then we get scores, which are basically cosine similarity, right? So it might happen that within a set of results, we get vectors belonging to the same entity. We take, in order to calculate the final score for this entity, we take the best match over all the fields that we got for this entity. Sometimes we add more weight to one particular field in relation to another, because we realize that they're a bit more important for search. All those parameters we can tune with simple Bayesian optimization and mean reciprocal rank as a target. So we run Elasticsearch to retrieve some results. We call it Milvus, and then we have to do the pruning. For this part, we do some weighting on different subscores, but we also utilize the features that we built in-house for these different entities that try to capture the popularity of each entity. So we just basically combine all those different subscores with different weights and select a small number, and that's how it works more or less. So we used search engines, and we got the list of these different entities with queries used for these search engines, and now the goal is to do the re-ranking, resolution, and selection. And the first part of that is to assign a score to each result, and then only we can move forward to grouping similar entities to equivalence classes, and then rejecting some of these classes later. So how does the first phase of re-ranking work? When we want to assign a score to each resulting entity, for that purpose, we use a rather simple approach. We use a cross-encoder model, which is a transformer-based model that you can import from sentence transformers library. So it works as follows. You get a query that you use, you get a prompt, which is basically something that describes entity result, the search result, and the model has to assign the score between 0 and 1 for these pairs to determine if there is a match or if there isn't, right? Yeah, let's move forward. How to train such a model? Training is not that interesting, really. The more interesting piece is preparing the data set for this problem. So we make use of labeled transactions, but it's not enough. This data set is really small, so we have to construct a bigger data set using some clever approach. So we have a huge database of entities. What can we do? So having an entity, we know, for example, what's the website of this entity. We can take its name, obfuscate it in many different ways, run the queries to the search engines that we use, and just check which result matches the website that we started with, right? This is the positive target for the model. All other results add up to the set of negative. So this is how you can train such a model. It proves to be really good. So, okay, then we have to match similar entities that correspond to the same underlying entity. We do it in rather naive way. We do it basically by looking at the URLs if they have the same domain and so on, because doing it in a smarter way is actually extremely difficult, right? If you search for Napoli pizza in Brooklyn, you might get one domain, which is napolipizzabrooklyn.com, but then you can get results from Yelp, for example, and there are so many similar restaurants that you cannot really tell them apart, but just looking at the text snippets. So then we assigned some ranks. We did entity resolution. Now the goal is to take out individual scores outside and have a score for the entire group of entities. How we can do that? So we came up with a formula that follows the intuitions, such as try to increase the confidence for large groups. That's something that we could call voting strength. Decrease confidence if other groups have high scores, right? So we just want to avoid ambiguity. And sometimes it might happen that some of these entities that we found, we know how we should proceed with them. So using the domain metadata database, we override confidence scores. Then, based on the threshold that we tuned during training, we discard some groups. So yeah, let's say we got groups of entities that belong to the same equivalence class. Then we still are hungry for more information. That we know what's the website, we know the names, we can look up some additional info and add it to those lists. After that, we merge them together to arrive at the final representation. So how do we do the entity enrichment? I know we like the word of enrichment. So we again use the search engines. Some of them are the same search engines that we used earlier, or we use our own internal database to find out tags, alternative names, some logos, descriptions, everything that might turn out to be very useful. We also are able to determine the location at this point of a particular entity based on the store ID. So for example, here you have a transaction spent Gigster at Loves 295, and we already know that what Loves is. We don't know their website, and using our entity store where we have mappings from store IDs to locations, we can resolve the location of a given transaction. Then, having a list of resulting entities, we try to merge them together to arrive at the final representation. So the name is chosen using a model that's rather a simple model, but it's fast to execute. It's based on some features that we constructed. But yes, this is simple and it's quick to execute and works really well. All the tags and the descriptions that we acquired are concatenated because we want as much valuable information as possible. But other fields like logos and so on, they're chosen based on the priority of the source. Some sources prove to be more reliable. We can trust them more. So that's what we do when we want to choose the final representation. And the last stage of the algorithm is to assign roles to the entities that we resolve. So in the original transaction that I used as an example, we had PayPal, Hulu, they got resolved. And now the goal is to say which one is an intermediary payment processor, which one is the actual merchant. And here we rely on heuristics, on clever tricks and statistics. We don't have a model for that. It has, because we can get really far with that at this point, and another model would incur quite considerable cost on execution. So for now, it worked really well. We look at some patterns, like, for example, when we see a star, like here between PayPal and Hulu, it might be very indicative that the PayPal is a payment processor. We also look up our labels store, because one of these entities might have already been marked sometimes as a payment processor or delivery platform. We can also make use of this information at this point. So this is a bird's eye view of the system, of its architecture. In the center, you see the entity search algorithm, which has two modes of execution. One's real-time with strict latency requirements. The other one is batch execution. In real-time execution, we make use of Triton inference server, where we have all our transformer models for fast execution. In batch mode, we run unexcified models in process. This core algorithm consults search engines. There is one additional internal search engine, which is OpenStreetMap, that we use to prettify locations that we sometimes find in transactions. And yeah, as I said earlier, we have Scylla database, where domain metadata resides, where we have all the entities, and the search cache. So here, I'm short on time, so I'll skip a few slides. Right, so we already described the system, how it works more or less, but then the problem is how to make it even better, right? So we constructed this loop, this feedback loop, that tries to continuously improve the quality of this system. So we have results data, like the outputs from our system, and we have some tasks that look at those outputs, try to analyze them, and construct labeling tasks so that people can look at it and add more labels to the system. Also, we have data quality engineers that they take reports from customers that look at the outputs and create those tasks manually. They, through this Ntropy dashboard, they also have a chance to hard code some behavior for very nasty and embarrassing patterns, right? So so this all of that forms a loop which makes our system better over time, right? We have more labels. We can, thanks to them, optimize search, but also extend our training data set, making our models more robust, and so on and so on. So yeah, that's basically all of the most important things I wanted to convey for this presentation.
Okay, let's thank Marcin. We still have some time for Q&A. Any questions? So I'll start here and then I'll go back.
Yeah, for the real-time model, how fast is it, and is it quick enough to fit into like a credit card decisioning system?
Yes, I think these models are not too big. They don't have to understand the full semantics of real world, right? They don't work with very complex queries, so they're fairly small transformer models. And on Tritons, they are really quick to execute, but I don't remember the exact numbers.
Yeah, so my question is, how do you deal with the ambiguity? Like, for example, when you said DD was DoorDash, but it could also mean like something else.
So yeah, for this purpose, you can take into consideration some external data, right? First of all, you might check how often in label data one particular pattern occurred. You can also take into consideration the market of the transaction, right? So for example, the same DD may stand for a different thing in the United States. It may stand for a different thing in Europe, right? So there is extra information statistic that you can utilize to disambiguate these patterns.
Just to follow up to that question, how do you deal with those monitors as they change and evolve over time?
Again, could you repeat?
So an entity might have a new name, or an old name may fall out of favor, and thereby changing the model.
The name, you mean like what if name of a given entity changes over time, something like that? So that's also why we have our own internal database of entities where we can, overwrite because someone reports that there is a problem, a name change, right? So, but also, as I said, we heavily rely on external search engines such as web search engines, and they usually have the data updated.
Thank you for the talk. So part of what you talked about implies thinking about context. And one part of context is who the transacting parties are. And one could imagine taking kind of network information or kind of graph models into perspective. Is that something that you consider?
Oh, yeah, of course. I mean, the complexity of the system may grow arbitrarily large, right? So here I presented you with a very flat and simple case where we're looking at a single transaction to get the enriched version in the end. But the reality is that we can look at the entire history of transactions of, let's say, particular underlying account, and it might be very useful in making our resolution even better.
I think you said you were creating like additional validation data by like obscuring words, and I just wondered how you arrived at those methods and what methods they were for obscuring the words.
Oh yeah, here. So so it's actually not that complex, right? Because we see so many different kinds of obfuscations that there is. I don't believe that there would be a model that would be able to generate all of them because they are so easily compressible. For this purpose, we built a utility tool that's based on some configurable probabilities, samples different kinds of obfuscations, removes some vowels, concatenates words, distorts name in different ways, but not in such ways that it would be impossible to really tell to really tell anything about the still. So we really had to tune this tool, but still then from this tool we get the query that we run against the search engines. So so in this process we still know if the query was too hard or not, right? Because search engines returned that result that we'd be interested or they did.
Okay, we have time for one last question.
Hi, thanks for the great talk. I would just be curious what the general source of data that goes into the model is. Like, is it coming from mostly bank statements, and also who your primary customer is?
So for the model, right? So in this case, when we consider the cross encoder, as I'm showing right now, most of the data is artificially created based on the entities that we have in our database. Some of the data comes from labeled transactions that we have in our database, which is very small. What else? What was your second question? Sorry.
Oh, sorry. Who is your primary customer?
So we expose the API. So our customers might be other banks, financial institutions that built on top of that some smart solutions.
Okay, let's thank Marcy.